Okay, before I go there, so let's go and summarize what we've seen. We saw single event blocking IO. That means each IO operation is blocking and returns a desired status or result. Okay, it blocks till that happens. Okay, and all operations other than write are synchronous. They block till the operation completes. In the case of write, we block until the data are in the kernel buffer. And then we say, we just want to know the data have reached there. After that, we just hope everything goes well. And if you're using TCP IP underneath, if the host doesn't crash, the connection doesn't, the computers don't partition into different networks, it will finish. Okay. Then we saw non-blocking IO. We went to this stage where we took the same signatures, we took the same operations, but we did not block. Okay. And each of these operations returned something. So that told us whether we got the desired result or how much of the desired result you got in case you're writing multiple bytes or reading multiple bytes. And you can look at the status to determine whether you should reissue the call. Okay. If you're going to reissue calls multiple times, then these calls better be idempotent. They better not have side effects. And actually, I should take that back because your read and write will have side effect. So it's only so I should take this back. Okay, but you should safely be able to execute this calls multiple times without getting unexpected results. Okay, so we saw that the long duration there was a long duration operation, the connect call. So that was broken into start and finish execution, and other operation was simply converted into non-blocking. Okay. And then we went into and so we are polling here, okay, which is not very good. So to avoid polling, we use the same operations, non-blocking IO, and we did multi-event blocking. That means we blocked for multiple events, one of several events to occur. Okay, so that was the select call that we saw. Okay, and to really define what we wanted to block for, we needed the registration keys and so forth that we saw in the previous slide. So whenever the select call unblocked, we process each enabled key by executing its operation on its channel. So in general, there can be multiple operations with each key. Here, I'm assuming there's only one operation. So you can just go and execute the operations that are enabled whenever you get back a key. Okay. So now let me continue the thought I had earlier. That if I was to give you these abstractions and you understand things the way I explained them, theoretically you can write any application, but what you will do in practice is go to the web and try to find a tutorial and see how these operations are typically used. Okay, and you'll see some sample application and you'll say, okay, I see how this is built. This is how my application differs from it. So this is the boilerplate code. This is the part I need to change, and so I get my program working. And of course, since you've got the theory, you understand what you're doing. Okay, so that's pretty much what I did to understand NIO, and that's what I told my students to do when I first taught this subject. Okay. And NIO is complicated. So the NIO standard is always the most complicated one, and it will probably be the most complicated one for you too. But it posed problems. Okay, so the ROCks tutorial told you how to build an echo application. So the same server could talk to multiple clients, but each client was independent. So when you sent a message M, it got a return value back, and nothing happened to the other clients. Okay. The assignment requirements were the Halloween simulation you have, and that, as you have seen, requires you to broadcast values. So if I send message M1, it goes to multiple different clients, and if I send more messages, they all go to different clients, and sometimes you, in fact, as we'll see in a later assignment, get back results. Okay. So it doesn't seem like a very big deal in terms of change, but it did cause a lot of problems. and students made many mistakes. So so let's go and see what we were getting from and the NIO tutorial and see whether we could do uh, retain those good things while removing what I perceive to be the limitations. So what NIO does is explains the NIO abstraction and also the limitations of its implementation, okay, which are not well documented. I'm just going by what this tutorial said about the limitations. And it also has an implicit design pattern. So if I give you a bunch of objects and tell you go build this application, it's going to be much harder than if I told you, hey, use this design pattern. For instance, the model view controller design pattern or the factory design pattern. So and so this tutorial gave you a design pattern, but it didn't explain it as a design pattern. It just gave you some code, and you could see that certain code could be borrowed into your application. So you had to sort of extract the design pattern, not explicit. Okay? So many students or some students had trouble understanding what was needed to be done to make the change. The design pattern was not explicit, and design patterns are good, but it's better if something is repeated. You could convert that into an abstraction that is reusable. And when people go and copy boilerplate code into their application, they're essentially saying, look, this is all reusable. So why not just build that into a library? Okay. So that was the design goal when I created the NIO manager. Okay, and we'll see there's limitations. Anytime you do something different, there's pros and cons. Okay, so we'll try to see the limitations too. So that's the motivation for giving you another layer. And I told you that there is a gap between what the design says and what the implementation seems to support. Okay, so the design allows you to create multiple selectors. I just looked at the API today, and I saw that it confirmed that every time you do the open call, you get a different selector. Okay, at least that's how I interpreted the call to be. Okay? And once you have abstraction with a method like select, conceivably, multiple threads can call select that method on an object. Okay? And there is this data structure so also the threads that block on a select may not be the same as the one that register or change the interest ops. Okay, but these two sets of threads need to share data. Okay? The thread that blocks need to know what the interest ops are, and so there's shared data here. And and so there are concurrency issues. And according to my understanding of the ROX tutorial, at least, the current implementation of NIO operations are not thread safe, meaning they're not atomic. Okay, so so if you have multiple threads that are blocking on a select, they're also sharing data structure. Who knows what that means if you are supposed to have only one thread at a time? And certainly this becomes a problem. Okay. So I gathered from the tutorial that to be safe in an application and to be safe in the assuming the implementation that existed when the tutorial was created, and I saw some other tutorials that seem to follow the same principles, a single selector should be created for an application, not multiple selectors. Okay, and the select call is powerful enough that the NIO layer is powerful enough that you don't need more than one selector. Okay, and this is the important one: a single thread should select on that selector and register and change interest ops that determine the blocking conditions. So we need to sort of follow these constraints. And it's not that everything is that only one thread exists in the application, because you do want to unblock a thread, the thread that blocks on a select call, if your interest ops have to change. So another thread can call wake up on a block selector thread and change the data accessed by the selector. Okay, so that is safe. There's no problem with that, and you can't do anything interesting without that. So the challenge then is how to create this abstraction. And whenever we design a new abstraction, there's so many different parts that there's no clear-cut answer to how that abstraction be created. But based on what I've seen in the interaction with you guys, we can probably narrow the design if I tell you that we're going to support callbacks. So let's go and try to figure out how could we create an abstraction that follows these constraints using callbacks. Okay, and so the key is that here what we've done is we've got an abstraction that allows us to register channels in operation pairs. Okay? And we added an operation that blocks until at least one of them is enabled. How do we change this so that we now have callbacks and yet we have no blocking? And when I first motivated non-blocking, it was John Ray, I think, who said that, oh, I've seen in JavaScript callbacks to get back the result of a function. So somehow callbacks are relevant here. So let's just go and see how much we can change this to support callbacks. Okay, so I've gone 10 slides without asking a question. So high time I did ask a question. And so time for you guys to concentrate. I can't see your faces right now, so I don't really know how carefully. Okay, so basically what we saw was that originally we were registering just a channel and an operation pairs, right? And what we now do is register not only an operation and channel together, but also a callback. So we register essentially a triplet. Okay. And so either you can say, oh, the operation and channel are already registered. If they already registered, how do we, like David said, but how do we associate the callback with the particular operation and channel? And you can get back a key and associate a callback with a key, but why not do it all directly? Okay. And we can do it directly or indirectly. The high level point is that these three things have to go together. Okay. And we don't need now to block. We meaning the application layer doesn't need to block any longer. With NIO, the thread that went and did the registration is also the thread that goes and processes the operation that is enabled. Now we say some system thread, just as an RMI, goes and invokes the callback. Okay. And that callback invoke gives the desired result and status we want, and it's invoked by separate threads. So as long as we're willing to have these separate threads, we don't any longer at the upper level layer need this blocking operation. The abstraction we will build, if we're going to build on top of NIO, is going to have to execute this blocking call, but our application layer doesn't have to. Okay? So that's one key idea in this abstraction. Yeah, and we'll see there's drawbacks here. The moment you start letting the lower level layer make more decisions on your behalf, things get less flexible. Okay? And we'll see the pros and cons of the default implementation I provide you. Now here's the secondary goal. Okay? So we saw that we have in NIO the ability to write and read byte buffers. Okay? So a producer process on one machine can write a byte buffer, and a consumer process can read the byte buffer. But are these, if you really are interested in processing chunks of data, like in your application, you want to go and process a whole command at one time, and you don't want to, you're not processing byte by byte, but command by command, are we guaranteed that what we read is what is written? And we saw that the answer is no, messages are scattered or gathered. Yeah, and that really does happen when I started doing my implementation, I saw that. So another additional goal was that, that bookkeeping is interesting, but it doesn't tell you that much about distributed computing as some of the other concepts you'll see here. So I wanted to relieve you guys from the task of doing automatic scattering. So that was another goal that, and we can use byte buffers. Byte buffers are an abstraction we already provided, and we can just use this abstraction to allow messages to be received in the same, to allow the written and read byte buffers to correspond. So my animations are a bit off here. So I'm hiding stuff from you. I'm building a layer on top. And the question is, what am I exposing to you and what am I hiding from you? That is given by the lower level layer. Okay. You still have to create your channels. You still get to determine, how many ports you have in an application, and each port corresponds to a factory or service channel. So that control you have completely. So you create the server socket channel, and also each client just can determine, how many which servers it wants to talk to, and so it creates a socket channels that are bound to those desired servers. Okay. So you know about these abstractions. You don't know about, so what do you not know? None of these operations you need to know. Okay. And that seems strange. I mean, how can we read and write without executing read and write data operations, and without providing the read with the appropriate data structure and the write with the appropriate data structure? Well, in NIO, we have the idea of expressing an interest in an operation, such as read operation, um, and making a call, right? Why can't we go and just combine these two things? That our registration implicitly goes and tells you what the gives you a call, it registers the callback, and that callback tells you both um, what operation you're interested in and what to do when that operation is executed. Okay, so this read call tells you what to do, and this tells you what event you're interested in. That this tells you the events in which you're interested in, and this tells you what to do when when the event occurs. So why not just we just have this register operation that has a callback that goes, and we can have different kinds of registration methods for each operation, and the callback will just replace the read call, okay? Or any other call. We don't have to create selectors ourselves. Okay? We're going to have a single selector. We're going to follow the ROC's philosophy of having a single selector. If you're going to have only a single selector, might as well have the system layer create the selector for you. Okay? There is only one selector, so there's no choice to be made. That means you don't have to do an open selector. Okay? Since you have callbacks, okay. So since you have a single select thread, might as well create the thread in the abstraction. What the thread does can be influenced by the application program, but the fact that it makes a select call again and again in a loop, that can be encapsulated in the abstraction. Okay? And since we have callbacks, we don't need to go and uh, deal with these operations directly. It's possible to have a higher level abstraction, and so this is just and this abstraction can reflect the typical ways in which these abstractions are used. Okay? So that's sort of the overview of the structure of the solution. And here's the API. Okay, the API you can see is not too many calls, and you can see that we have channels mentioned here. So whoever's using the API must have to create these channels and have access to these channels. We have these callbacks here, so that's consistent with what I said. This dot 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 means that this is an array argument in the call in the callee. You can provide an arbitrary number of callbacks for each event. And when you're doing a connect, you want to also specify the destination host and port. So that's not buried in the socket channel. So that's something else you need to provide. The connect call is not going to be made on the socket channel directly by us, because then we have to worry about whether it's returned the right value or not. So that's why it takes these extra arguments. And we have listeners. Write needs to know what to write. Okay. Um, the read can return something that is written. So we don't actually provide a read buffer here, and we'll see why not later. For efficiency reasons, we do this. but that has its drawbacks. And we can also have a closed listener that tells us when the channel was closed. Okay? And let's look at these calls even in more depth next. Okay? So this is our registration method for accepts. Okay, so we don't have a single registration method for all events. Okay, so the command and the interest op is buried in this particular name, enable listenable accepts. Okay, so we are binding this channel to the accept interest op here essentially, and we give the listener here. And what does the listener get? It gets back the channel we registered. Okay, so that we know which channel this callback is associated with. And after accept, what does one do? When the accept returns, it returns a socket channel, which represents a new endpoint. So that is a return value, and return values are just provided in a callback procedure and can be accessed in this particular procedure. Okay, and so we have the socket channel now to do other things on. And what other things can we do on this channel? Oh, before we go to that, let's go and look at it from the client side. So it's very similar, except that connect call now also takes the destination address and destination host and port. And we've already created a socket channel, so we don't need to go and get a socket channel in return that we haven't seen before. But we do get our socket channel echoed back. Okay. And two things can occur: either the connection failed or it succeeded. You guys might have seen that if you provide the wrong address, connect doesn't succeed, and you get back an exception. So if there's no problem, then all you do is all you get back is then the connected callback is invoked. So you're actually registering objects in Java. You're not registering procedures. And the previous objects we saw had only one procedure, so I just called them callbacks. But now you're getting this object that you registered, and in that object, this particular method may be called, or this particular method may be called, and this method is called if the connection failed. Okay, so you registered an object, not a procedure directly, and what is called is procedures. Is one of the many procedures that are relevant that are in that object. Okay, and the one that's relevant to the event gets called. Okay, here's the write. The write needs some data, not only socket channel, but what is to be written. And you get echoed back this socket channel and the buffer. And you also get an ID indicating which write it is. Okay, so you can have multiple buffered writes. And if you care about which write got really finished, you can look at the IDs, okay, to see which write it was. Okay, so we've done another 10 slides without asking a question, so time to ask a question. So you see here now the full interface. And I'm hinting here in this question that this is a producer-consumer problem. In fact, I'm hinting here that this producer-consumer problem corresponds to the device driver producer-consumer problem we've seen earlier. And that connection may be hard to make, so I had a question about it also on this slide, which I removed, but I kept this picture. So the question here is, how is this a producer-consumer problem? And if it's a producer-consumer problem, who are the producers, who are the consumers? We know there's a select thread involved here. Okay, I told you there's one thread here, so it must be a consumer or a producer. So that's a hint. Figure out which role it plays, and then we can figure out what the other parties are. Okay, so let's go to that question. Okay, and let me give the answer by making the analogy with the upper and lower halves of a device driver. Remember, the lower half is executed by interrupt threads. The upper half is executed by application threads. Okay. So what this does is it gives requests to the lower half. Okay. When this happens to be, say, a get call, the request is please tell me when you get data. You're not really transferring data, but you're just transferring a request saying, I want a character when it arrives. When you are the upper half is executing a write, then the upper half is saying, I'm interested in write, so I want to request a write, and here's the data that have to be sent. So the request is a different request, but they're both requests, and the lower half processes requests. And as you'll see later, I'm going to encapsulate these requests into an object that I call a command object. And those of you who've done futures in concurrency, a future is essentially a command object in many systems, okay, especially in Java. So what are we doing here? We've got the NIO manager upper half, and the upper half executes those routines that we saw, such as the write call that Jason identified. Okay. So upper half executes an application thread. The lower half executes in the select thread. Okay. So unlike the device driver case, uh, what we have a single thread executing in the lower half, and even in operating systems, sometimes we often have three layers where the lower half uh, takes its communicates with a centralized kernel thread, which communicates with the application thread. Okay, so this kernel thread here, the kernel thread corresponds to the select thread here. Okay? Gives commands to lower halves, and this processes the requests. Okay, and the commands identify the channel and buffer and interest hops. Okay, and in the case of write, the buffer exists. In the case of other operations, there's no buffer but just channel and interest hops. Okay, so this one. Uh, the lower half goes and actually registers the interest ops, really goes and connects the interest ops to the channel and selector, because we remember those have to be, these are not thread safe operations. So this is the one that actually goes and calls the appropriate method of the selector or on the channel to go and do this binding. Okay, so it's the one that processes the request and then calls the listener. And as Jason said, that is also calling a listener is also a producer consumer problem, but in our implementation is a single thread producer consumer problem. So the NIO manager is essentially an observable, and it calls the observer methods or the callbacks, and we should ideally have them be called in separate threads, but for simplicity, uh, it's they're all executed in the same thread. Okay, and I'll talk about how we can get over this limitation if it's a problem. Okay. So what we are enqueuing is our requests again, but these are called commands now because we've got a command object. Okay, so the NIO manager upper half enqueues these commands, and we have multiple kinds of operations. So we'll see that we have multiple queues, and in fact, for certain operations, the queue consists of only one command. Okay, but this is the general abstraction, and the NIO manager consumes these commands. Okay. So when we have a producer consumer problem, we have to worry about synchronization. We have to worry about uh, the queues getting full or the queues being empty. Okay? And we know how to solve this problem in general. We've seen the bounded buffer implementation. But we have some of the same problems we had with the device driver. Um, some things we can do that the full bounded buffer problem requires. The applications can block. Okay, and uh, they can also go and wake up selectors to make it unblock. Okay, when it blocks on the select call. Okay, and if the queue is full, they can block themselves. So these are the kind of things we see traditional producers do. Uh, the lower half can unblock the upper half. So the queue was full, it can make the full queue non-empty, non-full, and unblock. Okay, and it can also call select if the queue is empty. Okay, so that's also good. It just says, okay, I'm just blocking till I get something interesting, and it'll unblock when. Okay. But here's the problem, and this problem occurs because we took the easy way and did not uh, use a very pure approach to implement the second producer consumer problem. The listener method is executed by the selecting thread. Okay. We require that the listener method should not be allowed to block. So we put a constraint here that the listener method should not block. And I've kind of given you the answer, but let's go and see, try to understand why this constraint has been placed. Okay, so this is very much, this is like saying that our interrupt routine should not block or the lower half should not block. Okay, because listener method is invoked by select thread. Select thread corresponds to the lower half. So we are saying the lower half can execute the select method. That's okay, but the listener methods that it calls should not block. In other words, the select method should be the only method that should be called by the lower half. Okay. So why are we saying that? Okay. So the problem really occurs when there are multiple services to be performed by different callbacks. Okay, whether these callbacks are where there are multiple threads or not is another issue. In fact, with the NIO layer, we try to keep the threads low. Okay, but there are multiple logical things to do, and the listener method is an application provided method, right? So you're letting the application layer block, higher level layer block the lower level layer indefinitely. That means if you have, some listener method that is malicious, or erroneous, that's doing some, so again, I was talking of multiple channels. If one of the listener methods, if the listener methods, one of the channels is erroneous, then other channels will not be serviced because that particular listener method has blocked. Okay, so the only blocking call selection thread should make, I sometimes call it selection thread, sometimes call it select thread. Sometimes I might even call it selector thread. So they're all synonymous. So what we really want to do is uh, um, ensure that the only blocking call selection thread makes is select, and it should also execute the post select codes efficiently, because it is a single thread that is handling multiple logical activities. Uh, so it's really switching between multiple activities. So any one activity should not be hurt. Okay. So the unblocking is done by some application threads, and they can take forever to do the unblocking. And like Leo mentioned, we might even get into a deadlock where one thread is blocked. The thread that is blocked on a full buffer is the one that would unblock it, and now we have a deadlock because um, the previous request that the same thread had enqueued um, resulted in blocking of the selector thread, and the unblocking of that would be done by the same application thread. So we have this deadlock situation. Okay. So uh, the the uh, whichever threads are going to unblock it, they can delay service to other threads that exist in the application, or just other logical activities that have to be done. Okay, maybe they're all done by the selector thread. And if and so they can be starvation. If you delay somebody, then you can also starve. So that can also result in starvation in the worst case. So application listeners should not block or take too long as they delay or starve some other threads. And this, I'm really recapturing the argument we provided earlier when we went from single threaded producer consumer to multi-threaded producer consumer. Okay, and I'm kind of saying that, look, I took the wrong route, or I took the easier route in designing this interface. But why did I do that? Well, the whole idea of using NIO was to keep the number of threads low. And if I was to have a multi-threaded solution, then I would introduce one or more additional threads. And if somebody, and again, I told you a principle that was the variation of the Amdahl rule that was mentioned in class, that keep the usual case easy to program and the unusual case possible. So if indeed a listener method does need to block, then the listener method should go and execute the code that requires blocking in a separate. So it can use a thread pool or a new thread for blocking or slow calls. So by default, we want to keep the number of threads as low as possible. Okay. So the NIO manager does not use new thread to avoid thread overhead when not needed. Okay, so that's the sort of compromise. And you can argue that, you can argue about what is usual and what is not usual. Okay, and this I'm just using my instincts here. Okay, so let's go and try to understand this in more depth. Okay. So let's understand the right call in more depth. What we have here is so what we saw in the previous slide was that the right call took provided an output buffer to the lower layer for output. Okay. So when I designed the NIO manager layer, I had two choices. I could either copy the buffer that the application layer provided and use that buffer when sending data, or I could reuse the buffer. And there are pros and cons. You may or may not remember the pros and cons, but I won't repeat them because we've gone through them earlier. So should the NIO write buffer, the buffer that is actually provided to the NIO operation, be a copy of the buffer provided to the upper layer, or should it be the same? Okay. And these are the pros and cons, and the question really is, which way do we go? How do we sort of make our trade-offs? And if we go and allow it to be the same, I'm sorry, if we go and make it a copy, then we don't have to worry about the copy, the original being changed while we are sending data. Okay, so the application layer is easier to program. On the other hand, copy is inefficient, and the whole idea of NIO manager or NIO is to provide efficiency. Okay, so we are reducing the number of threads. We also want to reduce copy. Okay, so it's inconsistent with NIO philosophy. The NIO layer lets you do anything. Okay, you can build the NIO manager layer that provides this policy, or you can provide an NIO manager layer that provides the alternate policy. Okay, but like I said, when you start providing high-level abstractions, you have to take decisions, and this is a decision I decided to take because it was consistent with NIO. Okay, so again, the decision I took is not as important as the pros and cons. Okay. So the application buffer is not copied by default, and this is something you need to know because you're going to actually use this layer. So it's important to know this fact. It's also important to know the trade-offs and whether this is the right thing to do or not. Like I said, I use my instincts, which is not a very good argument. Okay. But it does show which direction I went. But what it does mean is that we should have control sometimes, and actually the NIO manager has a is customizable, so everything can be changed through factories, and these command objects that it processes are created by a default factory, and you can change the command objects to do something different. Okay, so it's not as if you want to change the decision, you get nothing from the NIO manager layer. Okay, you just change the appropriate command object for write buffer, and you get a different policy. Okay, we won't get into how we do that, but it is possible to do. And more important, if you have factories, you can change parts of the parts of your library without changing other parts. So that's the point I want to make here. Okay, and I guess the point I'm saying here is that when you're not sure of which is the usual case, or when the usual case changes for another set of applications, factories come to the rescue, and so this is yet another argument for factories. Okay, let's go and look at another aspect. Let me just check the time here. Okay, so we have some time. How do we make sure? I said, oh, I want to save you from the task of scatter and gather. Okay, so I'm kind of implying that there's some mundane stuff involved there, but there's also an algorithm involved there. There's also some technique involved there to make sure that we can, in fact, make sure that the application doesn't have to do gather scatter, that the unit read is what was sent. So let's think about this. Again, we've gone 10 slides without, or a few slides without asking a question. So if I was to tell you, hey, there is no automatic gather scatter, you have to do this yourself. And of course, you have to code it, but before you code it, you have to think about how you would do it. So let's go and share that thinking process. What would you do to make sure that this happens, given that the underlying layer, which is the socket and socket channel layer I've talked about, does not provide this guarantee? The underlying layer might scatter and gather. So you have to somehow use the underlying layer to go and provide the higher level abstraction. Okay? And I kind of hinted at the answer in the previous slide, but you guys might or might not have paid attention to it. So let's see what the answer should be here. So, like Jason hinted, we need to ensure that the socket channels we created are used only by the NIO manager layer, that we don't go and do our own writes and reads on top of it. Okay, if we do that, things will get messed up. So we send header information. Okay, so if we are sending 50 bytes, we send with the 50 bytes the number 50 before that, so that the other side knows how much to wait for. So the 50 bytes gets broken into two 25 byte chunks. It waits for both 25 byte chunks to arrive. If the 50 bytes gets combined with another 50 bytes, then it sees that it sees the first 50 and then sees the second 50, and it goes and separates the header information from the payload and goes and breaks it up. Okay, and that's how networking in general works. That's how this scatter gather works in general, and that happens at lower level layers also. Okay, so that was actually sort of the easy part. So send header byte buffer before application byte buffer. So then again, we are talking about NIO manager. We're talking about efficiency issues. So another efficiency wrinkle that is created here is, should we allocate a header buffer on each send? We can't use the same. So the header buffer was something that we created. Remember, the write buffer, the payload buffer, that was provided by the application, and we just used that byte buffer. Okay? The header buffer information is something we created, and we need to then decide whether we're going to create a new header buffer for each send, or somehow reuse the header buffer. Okay? And of course, as you can imagine, we're going to try to be efficient. So we have a fixed header pool which can overflow. Okay, this is important when you guys are doing your experiments. If you go and send 1,000 or 10,000, or even I think 500 may cause a problem. I think by default, even 500 events, sending them at the same sending them without waiting for them to arrive at the other end can cause problems. So I think I mentioned somewhere in my assignment how to go and change the size of the header pool. Okay? So the drawback here is that we've got a fixed header pool which can overflow, and so we have to be careful about how much. Okay. Now, our add read listener call is not giving any buffer as an argument, okay, and it gets back a buffer. It's not giving a buffer as an argument because we want to go and have um, for efficiency reasons, okay, and that's sort of what we're going to get into next. Okay, so let's assume that it's not giving an input buffer and see a secondary issue that arises here. When the NIO manager gets data, it gets data in some buffer it used to read the data, and then it provides the application layer with a buffer that contains the data. And that buffer can be the same as the buffer into which it read data, or it can be a copy. Okay. So the question is, what are the pros and cons of making this decision? Okay. And if it's a copy, then the listener can go and change it in arbitrary ways without affecting the lower level layer. But copy is inefficient. Okay. So what we do is we provide a single input buffer, and this input buffer there's a single input buffer used. So this is why it's a system that allocated this buffer rather than the application. If the application allocates buffers and gives it to the NIO layer, then we have multiple buffers created. So here it creates one single large buffer that is shared among multiple channels and multiple uh, multiple clients that go and enqueue requests for that channel for those channels. Okay. So here, I guess I answered the question that I'm posing here. So we can create new input buffer for each send output buffer, header data pair, but this is inefficient, but it makes scatter gather easier. So, when I say that I took a different choice, I'm remembering the time it took to do so also. So, but what we have is a single input buffer with complex scatter gather. Okay. So we have let's say we get one piece of data, and then another piece of data arrived there, and we have got two different. Uh, uh, so I guess what I'm trying to say here is that our input buffer can contain past messages also, and it can have future messages, and we want to really give the application programmer access to a subset of the data, a subsequence of the data. Okay, so that seems hard to do or impossible to do. We can't have it both ways. That different callbacks access different parts of the buffer, different sequence of the buffer. It seems we have to create new buffers for that. But in fact, as this particular uh, uh, piece of text says, that we can have uh, multiple views on the same. Okay, so how does that happen? We go and we have this sequence of bytes, and that sequence of bytes is associated with the byte buffer, and that byte buffer has a position and limit and capacity. We can use the same sequence of bytes and associate with a different byte buffer that has its own position and limit. Okay, so we can give the application the listener layer access to only a subsequence of the data we have. Okay, and there's this call called wrap that can create a new byte buffer from a particular sequence of bytes, and then we can go and muck around with its position and limit to go and make sure that the right access is given before we give it to the application program. Okay, so that's something else you need to be aware of, that you are getting a view of the buffer, and you shouldn't try to and that should be okay. The byte buffer abstraction should go and prevent you from accessing any other part of the buffer. Just make sure you don't write to that part. So to review, we looked at NIO, And we saw that there was this tutorial that I liked, the rocks tutorial, that described how NIO could be used. And there was implicit in that code that was presented a design pattern. It wasn't explicit, and explicit in the same way that, like, say, the model view controller is, where we describe it via diagrams and say, okay, this is the abstract idea of design pattern, and this is how it's implemented. And like I said, in the past, students had trouble porting their code without that abstraction. And there's an abstract way of describing patterns, and there's also a notion of an abstraction, something that automates something for you. So if something is a design pattern, it may or may not be automatable. But this particular design pattern I try to automate via something called the NIO manager. Okay. So that's the kind of good news, is that I abstracted it out. The bad news is that there's something else you need to understand. You need to not only understand how NIO works, but also how NIO manager works. Okay. So we started on NIO manager last time. We're going to finish it today, hopefully. And so the way to describe the NIO manager, there's many ways to describe it, but in general, when you try to automate something and provide an abstraction, you make some choices for the programmer. Okay, so there's a lower level abstraction that maybe is too hard to use and is more flexible than we need. And we go and say, okay, this is really what you need in many cases, and you make some assumptions about those many cases, and you provide the abstraction. And again, ideally, you'd like to allow that abstraction to be modified so that if some decision made by it is not something you can live with, you can change parts of the implementation of the abstraction without changing the abstraction completely. Okay, so I mentioned last time we have factory classes that do allow you to change different parts of the NIO manager. But let's go and see what the decisions are that are made by the NIO manager. And these are the decisions you have to live with in your assignment. So some of these decisions come from the rocks tutorial. Okay. Sorry. Some come from the rocks tutorial, and some I've made. Okay. And before we go to those decisions, let's go and see how NIO works in its generality, and then we can go and see how we go and narrow its use. Okay. And before we go in and look at NIO again, let me just put it in context, since it's been a while since we had the lecture. So we've seen really three paradigms for doing data communication, or what I'm calling remote assignment. Okay, one is what some of you have used in your 431, which is blocking IO. That means each IO operation is blocking. Okay, so we have 4 IO operations: read, write, connect, and accept, and they're all blocking. And they're not synchronous except for the write operation. Sorry, they're all synchronous except for the write operation, which blocks till you have space in the kernel for the write. Okay. And then we went to non-blocking operations, which was easy transition from blocking. It just said, look, we'll if the operation can fruitfully do something, it'll do it. Otherwise, it'll just return. Okay. And there will be some status information given indicating whether it was fruitful or not, so you can try it again. And what triggers you're trying again? Well, maybe you can just go and try again and again in a loop that maybe has a sleep call. So you're polling. Polling is not good. And also, but to do this, I said it was quite straightforward, not quite. We had to go and take a connect call and break it into 2 components. One that sends a message, and it is non-idempotent, which means that if you execute the same operation multiple times, you have side effects, and it's not equal to executing it once. And then there was a finish connect call that told you whether the connection succeeded or not. You can call it as many times as you want to, and it'll give the same result. Okay. And then we went to this NIO, which is harder to use, arguably, and it has blocking. Okay, so it's even though NIO stands for non-blocking IO, the IO is non-blocking. So each of these 4 operations, read, write, connect, and accept, do not block. They just return what they would return here. But it tells you when to go and invoke these operations. Okay, you don't poll for them, you go and do another operation, which is the select operation, which is invoked on a selector object. And selector object is associated with channels and operations of interest in those channels. And whenever an operation of interest is executable, then that operation is enabled. So it blocks until at least one of the registered operations is enabled, um, and returns tells you which of them are which of the registered operations are enabled. Okay, through a list of objects called keys. So at that point, you can go and take each enabled operation and execute it. Okay? So it doesn't really execute the operation for you. It just tells you which operations are enabled. Okay, so if you need to do a write, it doesn't know what write buffer you want to write. It does know that the kernel buffer into which a write buffer needs to go is free, one of the kernel buffers available, and then you can actually provide the write buffer. Okay, so this sounds not so hard to use. Um, so let's go and see now what decisions are made by the NIO manager that may be hard to implement. Okay. So some of these decisions, like I said, were provided to me by the ROX tutorial, at least my understanding of it. So we saw that the selector object is associated with a select call, and also with operations that connected to interest operations and channels. And these calls are not thread safe. Okay, so according to the ROX tutorial, so to be safe, we should have only one selector object in an application, and only one thread accessing its shared state. Okay, and so that's one of the decisions the tutorial makes. And what NIO manager says is, well, if there's only going to be one select thread, let's go and provide that in the abstraction in the NIO manager itself, and programmers don't have to go and write that thread as long as the thread doesn't do something uh, that is very application specific. So now, how do other threads communicate with it? How do other threads tell it that, look, there's something of interest here that you need to, so I need to go and change the interest ops. How does it, and and I can't myself change the interest ops because that is in the shared data structure. So I want you, the select thread, to change it. Well, there's a wake up call provided. So the select thread unblocks whenever the operation of interest is enabled, and also unblocks when explicitly unblocked by the wake up call by some other thread. Okay? So this is very important. So the other threads are application specific. This particular thread is application independent. So they have to communicate with each other somehow. So what is the nature of the data? And this situation is somewhat akin to you're wanting this Java to create a new thread. What what the thread needs to do is application specific, but how a thread is actually created in the operating system is application independent, can be system defined. So it's very similar, except we're not creating new threads, we're just dispatching work to existing threads. Okay? And that again is an idea that is not quite foreign in Java. There are thread pools, and where you do very similar things. You say, here's a piece of work I want to do, and rather than creating a new thread, you go and give it to some thread pool, which goes and does the operation for you. And you invoke thread pools in your you created and used thread pools in your assignment too. Here, the thread pool, the Java thread pools are more generic. Okay? Then we also saw that we wanted gathering of data. Okay, even though gathering of data makes our job rather difficult because we have to go and scatter it afterwards. Okay, uh, we want gathering of data for efficiency. So in particular, so if there are a bunch of pending writes, then all of these writes ideally should fit into one network message if they do fail, so that we don't congest our routers on the way and we don't send extra packets. Okay? And if you're going and trying to send chunks of byte buffers and process these chunks in the order in the units in which they were created, then you're going to have to send some header information. So for every write, there'll be some header information sent. It'll be really too bad if these two writes were sent in two different messages. Okay? So what we want to do is, once we start processing writes, we don't want to interrupt this processing of writes with any other operation. So we want the writes to be executed essentially atomically. Okay? So that's another decision we make in our NIO manager. Okay, so even if while doing the writes, if some new message comes in and enables a read, we will postpone processing of that read till we've finished these writes. Okay, just for efficiency. Maybe the latency reduces, so this is the trade-off. And then uh, uh, so the connect and finish connect operations, I shouldn't say finish, are executed a single time. So interest in them is expressed at most once with a single connect command object. Okay, we don't need multiple connect objects for a channel, because we're not going to connect the channel multiple times to different servers. Okay? And once that's for a regular data channel endpoint. We're really talking about endpoint in the client. In the server, we go and have the accept. We go and have factory channels and regular channel endpoints. And on a factory channel, all we do is accepts. So once we have gone and told the NIO manager, look, I'm at this point ready to process accepts, connect messages. So please wait for the accept op to be enabled. We don't want to do this. We are not going to change that. Okay. So once we process the accept, we'll go back and wait for another accept. So the interest in accept op will remain. Okay. So a single command object will suffice for that, as long as the listeners we execute in response to accept don't change. So that's an assumption made right now, that we will not change the listeners for different clients, for instance. And similarly with read, we're going to assume that once you're ready to read from a channel, you'll always want to read. You're not going to have phases in which you read and phases in which you don't want to process messages. Maybe there are applications that would need this, but I couldn't think of any, so I didn't add that facility. So a single command, and we are going to collect everything in one read buffer, so we don't have to go and have multiple read buffers associated with each read command, with different read command objects. Okay? And so the read interest of a channel once expressed remains for its lifetime, except during periods of writing. During writing, as I said, we are going to execute them atomically, so at that point we don't even enable reads. And after the writes are finished, we go and look at what was the interest of before the write started and restore those interest ops. Okay? So we're going to have only one command object for read also. So like I said, maybe this, we can't have phases in which we are willing to read messages and phases in which we cannot, but the system is modular enough that we can change it if we find it good use. For now, that's not allowed. And then there were some decisions made for programmability and efficiency. So I didn't want you guys to have to do scattering and gathering of data. So that's all done for you by the NIO manager, and that code is really messy, and I'm always surprised it's still working. But I think it's been used enough that it probably works. Okay. And for efficiency, there's only a single read buffer allocated, as I've said multiple times, and that's an issue. Um, um, and also, write buffers are used directly for executing writes. Okay, they are not copied, even though they can be changed before they are read. So here's an application. It goes and says, here are some write buffers to be written, and it doesn't block. It can go and muck around with the write buffers. If it does, then it's not guaranteed what data will actually be sent. Okay, because the select thread does not copy the data into its own buffer. So there's three levels of buffers here. There's the kernel buffer, for which the select thread waits. There's the select thread buffers, which it actually uses to transfer data to the kernel buffer. And then there's the application buffers. If you really want to be safe, the application buffers should be copied to the select thread buffers, which should be copied to the kernel buffers. Okay, but we live dangerously here, and we just tell the application that once you put a write buffer there in, please do not use them till you've got a notification that the write buffer has been processed. Okay, so there's a write listener call whenever a write buffer is used, and at that point it can go and reuse the write. And because there's a single read buffer, um, that read buffer's content, a view of the read buffer is sent to the read listeners, and once the listeners finish execution, those contents can be changed by the select thread. So if the contents have to live beyond the listener method, then they should be copied by the application. Okay, so again, we're living dangerously here because we care about efficiency, and NIO is all about efficiency. Otherwise, we'd be using blocking IO in sockets. Okay. So this is a pictorial description of what's happening. We have only one accept command, and that may not exist also. Okay, so we can have 0 or 1 accept command. When the channel is first created, there is no accept command till it's issued explicitly. Similarly, connect command, there's only one per channel. There's only one read command per channel. And there are multiple write commands, okay, one for each buffer that you want to write. But they're all collected together under one write queue object. Okay, so there's a write queue object, and it has sub-objects. So it itself is a queue object because it contains other objects. So this is a hierarchical situation. And this object exists because we want to do process all write commands atomically. So since each write command object has a separate buffer, we need multiple instances. And write command queue is a parent object, and it sets the interest op for write once for all the writes it can process. Okay, so it is responsible for changing interest ops, not each write command object, because the write command object does not know whether there's other write command objects after it. Okay, so we've complicated matters a little bit, okay, just to process things atomically. And as far as the select method is concerned, select thread is concerned, it knows there's a write queue object, and it just calls its initiate and execute methods. And the write queue object then goes and decides what to do with that. And its execute method calls the execute methods of its write objects till it can write no more. Okay, and we're going to see how that works in more depth a little later. So here comes a little later. We're going to use an example to illustrate how things work. And I'm going to take an extremely simple application. I can't imagine a simpler application, in fact. So it's a remote hello world program. So a client can send multiple messages to the server, and these messages are all strings. So this is string 1, and the server just prints the string on its console. So another message comes in, it prints that string, and the client can send multiple messages in a loop, and they get printed out. Okay, so this is the example that I talk about in your current latest assignment. Okay, so I described that example. This is the example that you will use as a template. So it's important that we go through this carefully so that you understand what to do in your current assignment. And this is the NIO Manager API I described last time, and we're going to see how it works in more depth in this example. So let's look at the server. Okay, I told you there's an NIO manager. Is that a static class? Is that a instantiatable class? So it's in fact an instantiatable class, and it's got a singleton object associated with it. So that's gotten by a factory. Okay. And not only is the NIO manager created through a factory, but all the commands objects that I talked about are also created through factories. And these factories can be set. So we are using a predefined command factory. So the factories return commands, and factories themselves can be chosen. Okay, so there's a factory selector. So we have a second level of recursion here. So we are going to use a predefined factory that takes as an argument an interest op. Okay? And this is the NIO manager. This is the server. The server is only going to be reading. It's not going to be writing. So this particular interest op tells you what operations it's willing to do in the steady state when it's not, well, it's not writing anyway, but what operations it wants to do after the channel is connected on that channel, and all it wants to on the created channels through the factory channel, and all it wants to do is the read operation. Okay. So I misspelled this, I guess. By the way, I'm still working on your check style, and I think I'm actually I got it working on my code, and I'm actually trying it on Ram's code right now to see how well it works. And I found some problems with Ram's code, in fact, through this. And one of the things that check style check does is make sure that you go and use components in variable names that are words in the dictionary. So had I used this on my own code, I would have found that I've misspelled this thing. Okay. So anyway, uh, the NIO manager also uses factories. So we first use a factory to create a server socket channel. So that's not something that NIO manager does for you. You have to do that yourself through the regular NIO layer. And one thing I didn't talk about earlier was that you can, once you've had a server socket channel, you can bind it to a port number. Okay, and this is how you do the binding. So here's your port. Okay, port number that was passed to this particular initialize method from the main class, from the main method, and it goes and creates something called the inet socket address, and it passes that socket address to bind operation, and now this particular factory channel is bound to that port. Okay, and of course the local host. And we're going to trace this operation. And now we call it an operation on the NIO manager, which is saying that, look, I'm ready to accept accepts, okay, and connect calls, and the and this is the listener you should call, and this particular class that I'm defining is a listener for all NIO operations. And that's not the nicest thing to do, but this is so simple, and this way I could keep it all in one. I could make the code shorter. Okay, so it's calling this enable listenable accepts. Enable listenable accepts is going to somehow create an accept command, and it's going to go to the selector and say, what's your factory? And it's going to get the factory and then go and say, okay, factory, give me an accept command. Okay, and that factory is going to take this particular operation and pass it to the constructor of the accept command. Okay, so that's what's going to happen, and we need to look at what this accept command really does, the command that's in this factory. Okay, and that's again the default command in the default factory. So you can see there's multiple levels of flexibility. Okay. So again, this is the get singleton call to go and get the NIO manager instance. And this read call, I mean, this seems unintuitive, right? We are giving to the accept command factory the read operation. Okay. Why not give it the accept operation? Well, we know the accept command knows that it has to initially go and do an accept. It doesn't need to be told that. What it needs to be told is what to do with the return channel when a connect message comes in. And this is the interest op. This is very important here. This is the interest op of the newly created channel after it's connected. Okay. So that's what this particular text is saying. Okay. So this is the initial and steady state interest of the server channel endpoint returned by executing except on the factory channel. So this may be a little confusing, but it works. And this is the bind call I mentioned earlier, which I didn't talk about earlier, and it binds. And this is not a call provided by the NIO manager. This is something provided by Java. And let's go and see what this accept command does. The predefined accept command does. Okay, um, it's got this value that was passed in the constructor, and the constructor also gives it the server channel as through the enable accepts gives it to the factory gives it to the command. But let's go and see first the initiate. So it doesn't need to be told. It says, okay, I know what the server channel is, so I'm going to register. I'm going to tell the selector that I'm interested in the accept operation on this channel. All these operations return true or false, and it says, I'm not going to fail. So if I reach this point, I'm going to return true. So what did the constructor do? It went and stored its two arguments and instance variables, and the NIO manager. So the NIO layer is something that's flexible. You can use it both as in a with blocking mode and non-blocking mode. So we are just going to make the decision for you. We're going to always set the blocking to be false. Okay? Uh, I'm sure this is configurable somehow, but this is what I found in my code today. So we're just going to make it false. Okay? It'll be easy to make it configurable to be anything that you want. So I can imagine an NIO manager library that says I'm in the blocking mode or non-blocking mode. And why would you do that? If you're really blocking, you should use a socket code. That's probably what I was thinking. But you might want to dynamically go from blocking to non-blocking. Once you have non-blocking working, I'm not sure why you would want to do it, but this would give you the flexibility, especially if you're going to do some performance experiments. So this is what this text is saying about the, and this is just reminding you of what this next stop is doing. And what does execute do? So execute is called after the select call unblocks and this particular operation on this channel is enabled. Okay, so these three conditions have to be met. So it says, okay, I know accept call will succeed at this point. So let me call accept. And when I call accept, I get a new channel endpoint. Okay, so I'm going to force it to be not blocking. And this next op that I stored, I'm going to make that the initial op of this for this channel. And if the application needs to do something additional, I'll call listeners in it, and I'll pass to them the channel that was returned. And in our application, the listener goes and registers a read listener for that channel, okay, which we'll see later. Okay, so this makes sense. And let's just go and confirm this is what's happening. So at some point, the selecting thread made called select to block. Okay, so when it starts up, the select call does some initialization and calls and traces the fact that it's making a select call. Okay, so that is a selecting thread. Then the main method starts doing its job. And one of the things it does is go and set the factory. So we trace that. It binds the channel, and we trace that also. It goes and invokes this method on the NIO manager, which we trace also. And this has a side effect of creating the accept command and putting it in the queue that the select thread can process. So it goes and puts that command in the queue. Okay, so this is so this was all done by the main thread, and the first call was made by the selecting thread. And somehow the selecting thread needs to be told, hey, there is an accept command to process right now. Okay, and how do we do that? The main thread after it enqueues it calls the wake up makes the wake up call. Okay, so that's done by the NIO manager library code. You don't have to do it yourself, even though this code is executing the main thread. So the result after waking up, so that wake up is called by the main thread, and that results in the selecting thread being unblocked, which we trace that. It goes and dequeues the accept command. Okay. and it starts executing. It goes and configures that to accept. Uh, uh, so it configures it to be non-blocking. So that's what the blocking configured means. Then it goes and registers the channel that was passed in enable accepts um, with the accept operation, and then it says, okay, now I need to wait again. I woke up this time because the application woke me up. Now I'd like to wake up when a connect message arrives from the client. Okay, so it goes into this blocking. Okay, so this is the main thread. This is the rest of the operations were done by the selecting thread. And the thing of interest, that is application specific, is operation accept here. So now let's go and see what happens after the connect message arrives from the first client. Okay, we haven't seen the client code so far, but that we can assume that the client code will correctly go and send a connect message. So at this point, again, it's unblocked, but now it's unblocked because of an IO operation, not because of a wake up call. Okay. And it goes and that accept command, it processes that accept command by calling its execute method. And the execute method goes and registers uh, with the same selector, the return channel, and the operation read. Okay. And it goes and um calls the accept listener. The accept listener goes and, which we'll see later, registers the read listener for the new channel. So that is traced. Okay. And now there's nothing else to do, so it calls select again. Okay, so this is client one post connect. And before any message is written, so and this is client one, and we know we can distinguish clients by um, the socket channel, that is an endpoint that's returned, and that endpoint, when you print it, has the host and port automatically created port number, and the port number is 61252 here. And this is what happens with the second client, and the code is all similar except that this number changed. Okay. So let's now look at the connect code. This is what we had to write. So again, we have we get access to the same NIO manager. We have selectors for connect commands also, and they also take um, um, interest ops as in the constructors, and we go and pass the interest op of 0 here. 0 means that, sorry, what do we, I can't see it right now. Yeah, we pass it 0. And okay. 0 means that the client does not read. So it is saying that, look, I don't want to do anything when I'm not writing. Okay. So when I'm writing, I know the write buffer will make it right, and after the writes are done, I want it to become 0. So that's why we're sending 0. 0 means no. Okay. So this time, we're not talking about factory channels. We are actually talking of creating endpoints, and then we need to go and make this connect call on the NIO manager, and we need to tell it, to which host and port to talk to. So that's what's given here. And we can also register a connect listener, and we register the same object here, which will go and process connects. Okay, all these things can return errors, so we have an IO exception. And I'm just printing out the stack tracing. Okay. So this is, again, this 0 is the interest op post connect. We know that before connect, we're going to make the connect command itself is going to go and set the operation to be connect. But after the connect is called, what should the operation be? And this is 0. Okay. So let's go and see what happens in the connect command. So it stores the next ops, okay, and so it configures blocking false, and it registers the connect operation, not this operation that was passed. Okay, again, I have a typo here, and it goes in the execute command, it goes and says channel.finishConnect, which is guaranteed to go and execute, finish at this point. It calls notify connect listeners, and then it goes and uh, registers interest in the next stop, okay, which was passed here, and returns true. And let's go and see what happened in the client. Like the server, it invoked the select call in the selecting thread. And as in the server, the main method went and set factories. In this case, the connect command factory was set, and it makes the connect call. So that registers the connect command, and that gets put in the queue, and then it goes and says, look, in fact, this was enqueued, and so this is the request, and this is the enqueuing, okay, and then it wakes up the selector. The selector wakes up, dequeues the request, okay, it initiates the connect call, and it registers the connect operation with the um, NIO manager, with the selector, and then call select, waiting for the finished connect message to for the connect message to for the return message to arrive when it can call finished connect. Okay, so this is really waiting for finished connect rather than op connect. Okay, we assume that connection initiation is always. We mentioned this last time too, that we always have a buffer to send the connect message. We assume that, so we don't have to wait for that. What we have to wait for is the finish connect operation to be enabled. Okay? And notice at this point the channel is unconnected. Okay, so when we print out the channel endpoint, it tells us what the status is. So when we first create it, it's unconnected. When we initiate, after we initiated the operation, it is connection pending. And in the next slide, we'll see that it's actually connected. So when it's connected, when the return message arrives, the select call unblocks. The socket channel is connected. And at this point, we go and see that the connect status has changed. And after this, after the listener has, after this, I forget in which order things happen, whether the listener is called first or we go and change uh, the operation of interest. But before we call select, it's very important to go and set this to no op. If we don't set it to no op, we are going to just poll continuously, okay, because the channel will always be connected. So it's connected, and we've set it no ops here. And once it's connected, the client can write, and this is how it writes. It has stored the socket channel in some global variable, and it just goes and sends byte buffers to the NIO manager. Okay, now what we're sending us are strings, and so are you. So we need a way to go and convert strings to byte buffers. And without going and allocating more memory, we can do that through this wrap method. Okay? So that's what's happening here. We're just saying wrap this in a byte buffer and send the byte buffer to this. And after we write to the byte buffer, we need to flip it. But fortunately, this wrap method will also flip it, so we don't have to explicitly flip it. So we converted the string to byte buffer. And what happens in the write command? So we could imagine a design where we have an initiate method for the write command also that goes and expresses interest in the op write. But as I mentioned earlier, we go and process write commands in batch. So every write command doesn't have to enable writes. So this doesn't really exist. So we have a constructor, no initiate method, and of course an execute method. And the constructor simply takes its two arguments, stores them in instance variables so that they can be accessed by the execute method. And the execute method writes the buffer and doesn't blindly return true as other methods have done. We may have something remaining in the buffer after the write because there wasn't enough space to write the complete buffer. So if the buffer could not be completely written, it returns false. Otherwise, it returns true. Okay? So execute returns false if it could not be fully executed correctly. And so the question becomes, how should the true and false values be processed, and who should process them? Okay, so what are they indicating to the rest of the world about how the writes should go? Okay, so to whom would this Boolean value be of interest, and what would that agent or module do with the return values? Okay, so let's go and make that the next question, and here we go. Okay, so as David mentioned, there's something wrong happened here, that the write wasn't completely done, but not an exception. This is something we should expect and retry. And we need to retry. And who's the we? Not the application in our case. The NIO manager takes care of this, thankfully. So you guys can relieve of this task. So if it's true, then remember there is this execute method in the write queue. Okay? That write queue says, oh, this particular command object was successfully processed. So let me go and try the next write command. And we'll keep doing that till it runs out of write commands or it gets false. And when it gets false, it blocks for kernel buffer to be available. Okay, so that is what needs to be done. As it turns out, what needs to be done is done by the NIO manager and not by the application. But we do see why we need to know this information. And here is that hierarchical object I talked about. It has references to these write commands, and its execute method calls these execute methods, and it's got a command. When we go and say, here's a new buffer to NIO, NIO goes and says, hey, let me find the right bounded buffer command object, and it goes and puts the right command in its queue. And after a write command has been processed successfully, it's removed from the queue. But if it is not processed successfully, it remains in the queue. Okay? And like I said, the execute command goes and executes the execute command of each write object. If that execute method returns true, it dequeues that object, goes to the next write object, and if it returns 0 saying nothing was written, it goes and keeps the object and doesn't dequeue it. Okay. So here's my bounded buffer. Every time the buffer becomes non-empty, its initiate method is called by the selector thread, and it goes and saves the old interest ops. It knows that it's going to set this to write op, and in the steady state, we don't want write op to be the operation of interest, so there might have been some other operation, including no op. It saves that operation every time it's called, and then it goes and calls these. It goes and does what I described earlier, and processes the command objects and didn't process them no longer. So a question at this point is, and it goes and whenever the buffer gets empty, it goes and registers the saved interest ops. Okay, and then goes and calls notify buffer empty listeners in case there are any. And this is very important here. It does not go and make the operations to be saved interest ops or op write, either here or here. Okay, and I was going to ask you that as a question, but let's see here. So if we go and make it here, then it'll keep blocking and polling. And if we make that the operation here, then we won't be able to execute the write operation atomically. And so we're trying to execute it atomically. And so we don't want any reads, for instance, to be processed. Okay. Okay, so let's go and see what happens here with the when we enqueue when we go. So here's what happened. The user typed "Hello World," okay, and then um, so did we see this code? I guess we did see this code. Yes, we saw that the string was processed, converted into a byte buffer, and then the write method was called on the NIO manager, right? So we sent the byte buffer to the NIO manager, and the NIO manager goes and creates enqueues uh, makes so this is the socket channel write request on the NIO manager, and it goes and enqueues two write commands. So the user entered "Hello World" atomically. So this really is going to see how much you've been paying attention. So why do we have two write requests when the user entered only one string? Our system can handle multiple write requests, but why are we going and using two write requests? And if you look carefully at the at the full message here, you will get the answer. Okay, so there's the header information and there's the payload information. So we've got these two buffers. Okay. Wow, it's thundering here. I assume it's thundering where you guys are too. Um, so then after putting those two buffers, it wakes up the selector. Selector unblocks. Selector says, "Oh, it finds that the buffer is non-empty, so it makes the interest op to be right." Okay, and then says, "Let me wait for a kernel buffer. Hopefully, it won't block at all. I mean, it'll immediately return, but just in case kernel buffers are scarce right now, um, it needs to ensure that that's not the case. So it may invoke select." Okay, and the select unblocks. When it unblocks, it knows that at least some of the buffer, some of some part of a write buffer or some command can be written. So it starts writing. And as it turns out, it goes and dequeues both requests and writes them both successfully. Okay. And then it goes and resets the interest op to no op, which was the initial op. Operation. And makes select, call select again. And if it didn't do that, and if it kept it at write op, it'll just go into a loop. And I think I wrote this a long, long time ago, but I'm sure I made that mistake and found this the hard way. Okay. And let's now look at the read code. So I told you this earlier, but I didn't show you that the accept listener goes and gets the newly connected server socket channel and adds a read listener to it, passing itself to it because it's also a read listener, the object. And here's the listener method for callback for read. It gets the channel on which it was that is read, the byte buffer that the system that the NIO manager maintains, and how many bytes are in the payload. Okay, and now it needs to convert the byte buffer into a string. Okay, and there's a complicated way to do it, and there is a simple way to do it. And I am using the complicated way. I'm saying, okay, create a new string, not out of the byte buffer directly, but I'm going to give it the message.array and the position, a position argument, and the length. And this is going to guarantee that I get the payload. So a question at this point is, we convert a string to a byte buffer, and I can use a simpler method if position was going to be 0. So there can be many reasons why the position is not 0, but can you think of one reason that can be answered directly based on some of the questions I've asked recently? Why might position not be 0? And why do we have to go and give this position directly rather than just tell it to use 0? And this is not completely a fair question because who knows what I'm doing underneath with position, but based on what I've asked before, you can probably make a good guess as to why that's the case. Okay? And if nobody else answers, Jason, I'm going to make you responsible for answering, because you should be able to answer that based on your previous. So as David mentioned, as I said earlier, a single read buffer for all received messages. And the view sent, it could, as I said, it's not a fair question, because the NIO manager could go and make position point at 0. It creates a view. But it says, okay, just in case you want to know what the header was, okay, let me just put the header with this. Because I'm giving you enough information to ignore the header. So I'm giving the flexibility to see the header. So the view sent includes a header buffer associated with the payload. And that's why position may not be 0 as okay. So this is my read command. It has got no initiate method. It just stores the channel. And every time its execute method is called, it reads the buffer. And this calls a method to see whether the sent data has been completely read or not. So it might have got the header buffer and only part of the payload. The payload may be really large. So this is, all this stuff is handled by extract buffer. Okay, so when I told you that I'm always surprised the stuff works, this was a really complicated piece of code. But assuming it works, it says, okay, at this point I know that the send data was completely received, so I'm going to call notify read listeners with the message that I create out of the read buffer. Okay, so the read buffer and the message are two different objects. So I'm just showing you part of the code that's executed. Okay. So the question then is, how did this read succeed? I mean, who set the read interest op? We don't see the read interest op being set by anybody here. The read command is not part of any bigger object that sets the read, and yet the read must have been expressed as an interest op. So again, if you've been paying attention, we've seen the answer. So when was what made sure that the read interest op in the server actually got set before uh, before or after even the read message arrived? It has to be set at some point. Okay. So basically, there is a steady state operation, and then there's the write operation that is set during periods of writing. So in general, a connect, I mean, in our case, it is the server that's reading, but in your case, the client will also read. So the connector accept set the initial and steady state interest op, and write buffer queue reset the state after setting it to write op. So the read op was set by the accept command, yes, and was reset by the write buffer queue. And read command does not initialize or change read command. Okay. I should really say it should not initialize or change the read the interest op. Okay. So read command does not do either of those two things. So read command is oblivious to it just assumes somebody else is doing the right thing for it. Okay, so let's go and see what happens. And the server, after the client goes and does the write, the select gets unblocked. And at this point, the execute method is called, and we read the buffer. We read first we read the buffer, and so we do these operations where there's the header read, and then there's a full message read, and there's the sort of initiation of these two reads, and then we go and call the read listener, and the read listener goes and prints out, extracts the hello world and prints out this message here. Okay, so this was actually printed by, this is not a trace statement. This was actually printed out by I didn't show you that, I didn't focus on that, but if you look at the code I showed you, this is what gets printed out by the read listener. And then it says, okay, I'm ready for more reads. Okay. So I thought we would finish, and we did um, ahead of time. So we're going to finish actually 10 minutes early. So let me just summarize. When I first taught the course, I told you guys that I just gave the tutorial to my students and said, just go and follow the pattern there and extract the pattern. And now I've spent this full lecture and half a lecture last time. I've had to work quite hard to abstract concepts out, and I've done this abstraction twice or three times. When I first made the NIO manager lecture, and then when I modified last time's lecture, and then I spent all day today doing this. So hopefully things will be easier, but you can see why those students had this problem. And so if you think that you're suffering in the course, others have suffered more. And so hopefully your assignment 6 should go very smoothly now. Not only did I go and make this abstraction, but you don't even have to look at this video to go and understand how the NIO manager works. I wrote down a description of all of this in the assignment in the end, so you can just read that stuff. You may need to go back here, but I don't think you will. And uh, and we saw very explicitly what decisions are made by the design pattern abstraction. Okay, so those are things I might ask you exam questions on. So it's not as if you don't have to know this stuff. The interesting part is not the API as much, which is easy to use, but how the API is working, how to what arguments to send to the various calls, and to know what to send, you have to understand what's going on underneath. So I think the next slide is the end. Let's see. Yep, that's the end.